Hello, everyone, and welcome to this webinar from the IHS Technology team. I'm Joanne Emery. I lead the webinar group, and we want to thank you for joining. Our focus today will be on multi-layer packet optical transport systems, and the panel will be looking at how multi-layer architectures can provide simpler, more efficient networks for operators. Our webinar is co-presented by IHS and our partners Corient, ECI Telecom, and Fujitsu Network Communications. So just before we start the presentation, I'm going to quickly review some features on your console, and then I'm going to let you know how you can participate on the discussion. So first thing, the console that we've preloaded can be customized, so you should be seeing your webinar slides right in the middle of your screen. I encourage you to maximize the slides for better viewing. You just need to click the green box in the top right corner of that window. You can also click and drag the bottom right corner of your slide view or of any window to resize for your own preference. You should also be seeing a row of buttons running along the bottom of your screen, and these widgets contain much more information and a lot of options for you. I will call out that resource list widget. This is the one that looks like a little file folder, and this is where you can find the downloadable version of the deck from today's presentation. Also, in addition to the deck, we have a number of other items posted up, including an IHS white paper, there's product specs, and there's links to a lot of information and background on our topic today. All these items are posted right in the resource link, so please check that out during the session. And one other widget I'm going to call out is our help area. That's the icon with a question mark icon, the question mark on it. And it's on the far side of your widget lineup. If you have any technical difficulty, just click on that help widget and you can find a lot of answers to common technical questions. And now some ways you can participate. We do have a Twitter feed running on your console. So you're going to see tweets pop up and you can view and tweet right from the webinar. We're using a hashtag PacketOptical today. And finally, I'm going to mention our Q&A session. We do want this to be an interactive webinar for you, and we want your input. So at the end, directly following the presentation, the panel will take your questions. You can enter questions or your comments anytime during the session. Just use the Q&A box right on the left side of your screen. The panel is going to be monitoring your input right throughout, and we'll try to get to as many questions as possible, so get your questions in early. And also any questions we can't get to on the webinar, the panel will follow up with you directly. And with that, I do want to introduce our panel. So leading our discussion today is Andrew Schmidt. Andrew is Research Director for the Carrier Transport Networking segment at IHS. And from Corient, we have Harold Bach. Harold is CTO for Technology Strategy at Corient. And from ECI, we have Jonathan Homa with us, and Jonathan is Director for Portfolio Marketing at ECI Telecom. And rounding out our panel is Mike Sabelhaus. Mike is Principal Optical Solutions Architect at Fujitsu Network Communications. And with that, I'm going to turn the controls over to Andrew, and we'll get started. So Andrew, to you.
Thank you, Joanne. Good morning to all of you, and thank you for joining. Today's agenda, I'm going to kick off the discussion with some of the market trends surrounding multi-layer optical equipment. And then we're going to hear from several of our sponsors, starting out with a discussion of some of the challenges that are involved with network convergence. And then following that, go into a more deeper discussion of exactly what's changing in traditional transport architectures. After that, we'll talk a little bit about some multi-layer networks in the field and what some of these deployments look like. And at the end, you'll have a chance to hear from each of our sponsors about their individual approaches to this market. I'll wrap with some quick conclusions, and there will be Q&A at the end, hopefully around 15 minutes or so. I encourage all of you, as you have questions, to just go ahead and use the interface and input them, and we will get to them at the end. So with that, why don't we go ahead and get rolling here. Now, packet optical as a term is been kind of abused, and so I think it's important to talk about exactly what packet optical means in the context of multi-layer networks. And the way that I define it and the folks on the call define it is multi-layer packet optical systems are hardware that converge layers 0 through 2 into a single hardware and a single management domain. So having a single piece of equipment that can do everything from optical switching via ROADM all the way up to the Ethernet layer. So these are systems with support for all of these functions, not just Ethernet, not just transport, but everything in a single system, and ideally managed with a single management layer. And this is a major transition from the way networks are built today, which is the network you see on the left. Now, ideally, when you put these types of systems into practice, you yield simpler and more efficient networks. And in this network diagram, you can see a network that has many, many different customers, both external and internal customers. So if you take, for example, a large service provider, they don't have just external customers, but they have multiple internal customers. They might have broadband connectivity. They have connections for wireless backhaul. They have their own IP and MPLS networks. And packet optical multi-layer technology is ideal for converging all of these separate networks that are essentially balkanized today into a single unified transport network. Now, some of the guiding principles behind multi-layer networks and packet optical that are really crucial is when you look at the type of equipment, it really varies depending on the network location. The further you get towards the edge of the network, the more important you really have for layer 2 intelligence. And as you move more towards the core, layer 2 switching becomes less important and becomes more about traditional circuit management. And at some point, when you get all the way into the core, you really need to move more into the domain of a true layer 3 edge or core router. What you're really trying to do is collapse the Ethernet and other layer 2 functionality into the optical layer. And you're not trying to compete with the routing layer. And as I said earlier, you really, as you move more towards the center of the network, you're really trying to just use the benefits of StatMuxing to get greater efficiency out of your network, as well as collapsing multiple transport networks into one logical domain. As part of this process, we can't really compromise traditional transport costs. So the idea is to leverage the economics of Ethernet, the low-cost components, and all of the software that's out there to essentially add and inject the layer 2 functions into the optical layer. OTN is a critical component of multi-layer networks. You cannot abandon layer 1 transparency and functionality. There are some service providers that have that luxury, but most do not. And I think finally, most importantly, packet optical is really a big catalyst for multi-layer network management. And we're going to talk about that today and the role that software-defined networks can play in this area. And with that, I'm going to hand it over to Mike Sabelhaus from Fujitsu, who's going to talk a little bit about the history of photonic network evolution.
Okay, thanks, Andrew. So what I'd like to do is just spend a few moments here talking about the evolution of the POTP and where we see it going also. Obviously, back in the early 2000s, we saw the static ring network, basically FOTM, generated. This network actually in the mid-2000s migrated to more of a WSS-based ROADM, what we call more of a static mesh type network. You had the invention of the WSS and the kind of migration from the 1x2 switching technology that was in the early static ring networks. As we migrate to the 2010, 2008 to 10 time frame, we see more of a dynamic mesh network. This actually introduced more coherent optical networking, which is one of the key features that we see as migrating to the next generation portion of the network. Integrated OTN-based switching, not only doing just basic aggregation, but actually providing OTN switching function in the network, giving you the ability to not have to decode every circuit that goes through, but you can actually do the switching at a switch layer and pass traffic through that goes downstream. mesh restoration, being able to do more of a one-by-one and one-by-n type, and then control plane introduction. But what this leads us now is to what I call the future of POTPs. That is the flexibility, the dynamic mesh network. That is the next generation ROADMs, being able to actually do command control of these ROADMs on the fly, being able to turn up services in a matter of minutes and not months, so to speak, by being able to simply pre-provision some of the transponders and provide that connectivity through, say, a software base such as SDN that will take you into the next phase of doing quick turn-up, quick changes in your network. More spectrum-efficient transmission. These are things like being able to do super channels and doing better filtering in the DSP technology that gets you a tighter spectrum. So being able to transmit 100G not on that 50 gigahertz ITU grid, but actually doing it in 37 or 38 gigahertz, so better spectrum utilization there. Obviously, optical reoptimization, doing 1 for N and being able to use some of that bandwidth that you would typically use for protection, actually use it for transport. SDN-enabled, modular, virtualized type functions. How can we virtualize more of this network as we migrate the system? So let's look briefly at some challenges of network convergence. So what we're seeing today is the industry dynamics itself are changing. We're seeing network and IT converging. Things like equipment. People have done proprietary embedded protocols. Being able to, and the competition itself has provided, new dynamics where there's been a request for more open architectures. People can actually deploy equipment faster and make the changes faster in the networks. This has really signaled more of an open plug-and-play type architecture structure. This has led to commoditization and sometimes disaggregation of functions in the network. The network themselves. Over the years, traditionally, IP networks were very static. You want to build a SONET network or an SDH network, and that was an overlay. And so what you see that for many years, the layers and layers of static networks have been added in the network. The POTPs have actually done a great job, as Andrew stated, being able to converge a lot of this together. This also helps with the speed of deployment. No longer do you have to build an overlay network, but you can actually just add cards into the existing system and build this. Long life, slow service activation and creation. What we believe is a very elastic and automated network is here to enable this quick turn-up of services in the network. Again, competition, speed of services coming up are being felt all across the network. You have some of the over-the-top providers versus some of the classical carriers actually competing for these services and competing for bringing up these services much quicker. And then finally, providers themselves, cloud-based architectures, network-attached storage, doing data center interconnections. A lot of the data centers, as we know it today, are becoming central offices and vice versa. Central offices are looking more like data centers. And so there's a real key point here of providers needing to add new connectivity, speed of connectivity, data center type connectivity in quick-to-use boxes. And so we believe that this will actually provide some new technology out there that will allow you to migrate the network using POTP platforms. The key point here is SDN, NFV are key software changes in the network, and POTPs, both of these are long-term disruptive technologies. So just looking at a few of these drivers, one of the service providers that we deal with basically said, Mike, everything we do is about the internet, everything we do is about speed, everything we do is about cost per bit, and everything we do is about convenience for that customer. So what we need to do now is look at the ROADM network itself. There's aging ROADM networks. There's a lot of operational complexity, lack of automation, and being able to provide a much reliable, lower total cost of ownership. So provider challenges here: how do you solve complex service activation? How do I do a services evolution so I can actually bring services up? How do I connect these clouds together? And how do I actually have more OSS agility in the network? So now I'm going to turn it over to Jonathan at ECI.
Well, thank you very much, Mike. So I'm going to talk about revenues, which are really the clear #1 priority for service providers. Now, vast rivers of traffic from cloud-based services clearly are having a profound impact on telecom networks, but I want to point out that not all clouds are the same. More conventional type of cloud services, what I call in the diagram centralized cloud services, to date have had the largest impact. These services, such as hosted applications, video streaming, storage, well, they're not particularly sensitive to latency delays. So one of the things that we've seen is that the people providing these services have been very successful at delivering these services over the top of the network. And as a result, the network itself is not very well positioned to provide value add for these services. However, you still want to be the transport provider of choice for these services, particularly to the well-paying enterprise customers. So I think that's imperative #1. On the other hand, there's another new breed of services emerging, which are called edge cloud services. These services, some examples are smart city services, machine-to-machine communications, Internet of Things on the horizon. They tend to be deployed in microclouds, or to use a technical term, hyper-converged clouds that are closer to the end user. Now, typically, these services are more sensitive to latency delays. And as a result, and we'll discuss a bit more about this later, there's a greater opportunity for the network to provide value add to support these services, perhaps through some not only connectivity, but also some platform services. So I'd like to summarize the challenges as follows. The #1 priority is to raise revenues, to be the preferred connectivity provider to enterprises for hosted applications, and to seize the opportunity to be the preferred connectivity and platform provider for edge cloud services. And all at the same time, let's not ignore, yes, we do need to continue to reduce OPEX and CAPEX, and more, we need to start taking a look at the network as a whole and to do all this optimization, not one layer at a time, but all these layers simultaneously or concurrently, which is really the focus for our discussion today. And with this, I will now hand off with some more detail to my colleague, Harold.
Thank you very much, Jonathan. As we try to optimize and converge networks and network layers, we do need to look at the trend driving changes in networks. And the most fundamental change in networks right now is the massive introduction of data centers, which are based on the disaggregation of compute, storage, and switching functions. As a result, networks are changing from a classical router-centric network design towards a network that is built around those data centers. Well, this trend means that there is an increasing number of data centers within carrier networks and also an increasing number of peering points, particularly in metro environments. This new network enables new, more, and higher bandwidth applications. It needs to support new and changing traffic patterns. And also one of the results of this data center revolution is that there are new business models and a new ecosystem that has formed, for example, around cloud services as well as software platforms or infrastructure as a service. On a network level, these changes mean that the traffic between data centers, and particularly also between data center and users, is increasing rapidly. Looking at this increase, within this increasing traffic, basically metro traffic growth is a very, very large part as the data center-centric network causes much larger east-west traffic between data centers or peering points in metro. Now, what does that quite revolutionary change mean for the network itself? Now, if a network architect today thinks about how to build a network, you will think in categories of circuit versus packet switch networks. And this very fundamental decision to go one way or another actually has strong implications on the network going forward. A circuit switch network clearly separates different users' traffic. It ties very nicely into installed multi-technology and multi-service base. It's simpler to operate, but it also is a network that is based on peak traffic requirement in each connection. That means it poorly utilizes the installed capacity, and it cannot aggregate clients efficiently. A pure packet network, in contrast, provides efficient statistical multiplexing and aggregation, but it has its downsides as well. It's very difficult to use with a TDM installed base. It can be complex to operate, and sometimes it's difficult to use when there are organizational boundaries within companies. So whatever a network architect decides, his hands will be tied in the network evolution by the issues and drawbacks that this decision brings. The question is how do we overcome that situation? And this question actually is essentially what we want to look at in the next section as we discuss new approaches to network architecture that can solve the challenges we see in current networks. So, what is that better solution that we are looking for? Instead of using individual technologies that tie our hands and result in limitations on how the network can evolve going forward, we need to combine the different technologies into what I call now a universal transport platform. A universal transport network basically provides the right combination of the different technologies of OTN, packet switching, and optical capabilities needed within a specific network to remove limitations in scalability and efficiency. So, as a result, a universal transport network will provide the flexibility we need to evolve networks in the changing network environment that we have to work in today. Next, I would like to look at what is a universal transport solution in this context that provides an efficient way forward. A universal transport solution basically needs to interconnect and aggregate packet and OTN traffic into large transport pipes and also provide high-capacity handoff towards routers or data centers. And basically, that does mean that in practice, on a sub-wavelength and sub-interface level, the packet and TDM traffic needs to be efficiently aggregated, switched, and forwarded. This capability basically maximizes interface and wavelength utilization, and it greatly improves network efficiency by that. The key to this efficiency is that a truly agnostic switch not only provides what I would call any service on any port, but really enables every type of transport service on every and within every port. At this point, I would like to hand back to Jonathan.
Thank you very much, Harold. So I think what Harold did was provide a sort of a broader view, and I want to focus here on one particular element which I believe is going to be essential towards network optimization. So network optimization and flexibility ultimately depends. It's nice to have the software control layer, but unless you have the elements to control, you can only go so far. So one of these key new elements is a new breed of multi-layer switches. These switches use a universal cell-based fabric that have the ability to handle both layer 1 optical data unit switching and layer 2 packet switching, both of which are very prevalent in our network today. just to give an example of how this works, so with layer 1 switching, there is an exact mapping of clients into the switching slots. So in this example, for instance, we can see 10 layer 1, 10 gigabit Ethernet client interfaces that will fit precisely into a 100 gigabit per second network interface. Now this kind of switching is becoming increasingly important with the advent of high capacity 400 gigabit per second network interfaces. These interfaces are quite expensive, so what we want to do is ensure that we have maximum fill on these interfaces with the lower speed clients, whether they're 1 gigabit, 10 gigabit, or even 100 gigabit per second interfaces. Alternatively, layer 2 services are becoming more important with carrier Ethernet that extends packet connectivity from the LAN across wide geographic areas. With layer 2 switching, because this is based on statistical multiplexing technology, more interfaces can be accommodated. Both types of switching support network efficiency in terms of maximizing resource use and for providing the underlying network flexibility for fast provisioning and dynamic restoration. Most important, I want to emphasize that both layer 1 and layer 2 switching can be supported on the same switch, with an ability to support different traffic mixes as demands change over time. So, for example, we can expect to see over the next few years an increasing weight of layer 2 traffic as more carrier Ethernet solutions are deployed. And I'm now going to hand back to Andrew.
Yeah, thanks, Jonathan. So at IHS, we conduct surveys of service providers several times a year, and we ask them about their plans for deploying new types of equipment and adopting new technologies and architectures. And in line with what Harold and Jonathan were talking about, and that is moving a lot of the packet functionality right into the transport system, we've asked service providers about their plans to use either dedicated routers or packet switching in multi-layer equipment, both today and in 2017. And what we've heard from service providers is that over the next couple of years, they're expecting to do less packet switching via dedicated routers and start to use more multi-layer equipment to provide some layer 2 switching in packet optical equipment in order to reduce costs and simplify their approach. So one of the challenges with this transition is the management of this type of equipment. You can no longer silo each of the transport layer and the layer 2 area and the router layer. You need to have a management approach that can balance the use of one layer versus the other and decide when it's best to switch traffic optically versus layer 2. So one of the key solutions that's being proposed by vendors is software-defined networking and centralizing the control of the network in order to gain greater efficiency. And we also ask service providers, there's so much talk about SDN. How important is it really? When you're making a decision today to buy a vendor's equipment, how important is their transport SDN strategy in affecting your decision? And this year, half of them said it was very important. And what's notable is that it was up pretty sharply from 2014. So software-defined networking and vendor approaches to this area are becoming increasingly important in how service providers are making their vendor decisions. And with that, I'm going to switch back to Jonathan, who's going to go into a little bit more detail about SDN and NFV and the benefits of those architectures.
Well, thank you very much, Andrew. I find it fascinating that SDN and NFV are so frequently paired together, they seem inseparable at the hip, that you would think they're twins. While in fact each of these technologies or architectures or solutions in fact have quite different origins and solve different problems. However, it turns out that they're highly complementary of each other and in fact are destined to provide a whole which is greater than the sum of the parts. SDN, by centralizing the control function, has a capability to calculate and direct connectivity across multiple network layers in real time. By having this holistic view of the network, it's incredibly more efficient at handling multi-layer architectures than a diverse set of network elements that are each talking to each other independently and try to figure out the best way to transit across the network. NFV speeds up new network service deployment. What it does essentially is replace dedicated network appliances with software running on standard commercial off-the-shelf servers. It's particularly adept at functions like security and policy management that can perform decision-making on processing streams of bits. In the diagram, you'll have noticed that we use the term TNFV, or Transport NFV, and what we're doing here is signifying network function virtualization, which sits in the network and serving multiple customers. By using open interfaces, open source software, open ecosystems, SDN and NFV have the potential to emulate in the telecommunications world all the service and cost benefits that they have already demonstrated to a great extent in the computing world. So there's a huge expectation on them. A final point that I want to make here is that as we roll out SDN and NFV solutions, it's really essential that they can be deployable in a phased manner so that service providers do not need a forklift replacement but can gain benefits over time. For example, it should be possible to provide applications like bandwidth on demand, as one example which is used quite frequently and in fact is quite valuable, that can run initially in a non-real-time mode through network management systems, but then so long as these SDN applications are open and use things such as RESTful interfaces, they can be ported seamlessly to run in a real-time mode over SDN controllers as these type of control devices roll out. And now to provide a bit more detail on this, off to Harold again.
Thank you, Jonathan. Within this framework of SDN and NFV that Jonathan just introduced, I would like to look at one particular aspect of SDN, and that is the question: how do we set up and operate this increasing number of individual connections or flows within networks? So classical and predominantly manual processes, as they've been used in the past, are clearly not practical going forward. And so, in order to use the increased flexibility and efficiency provided by multi-layer or universal transport approaches that we've discussed so far, we need to tie them seamlessly into the operational software environment that is forming in today's data center-centric network. This environment consists of applications running on top of orchestrators and SDN controllers, which then in turn run the underlying infrastructure and hardware in a fully automated way. SDN controllers running transport networks in this environment in particular provide an abstraction of a sometimes rather complex packet optical network. They provide automation for that multi-layer network, even across multiple vendors and network domains. And by that, they enable a truly dynamic and automated end-to-end network operation. I think this is key to make this type of network work. And next, I would like to hand over to Mike again.
Thanks, Harold. Appreciate the intro. And what I would like to talk about briefly is, just as Harold was talking about SDN, NFV, the virtualization, abstraction, one of the things we see happening in the industry is a move towards, again, the open architecture, the open pieces. Take, for example, the typical POTP platform being deployed today has switching functions, transport functions, WDM wavelength functions, shelf controllers, and literally the form factor of the shelf dictates a lot of the space, the power of the thermals in the system. It dictates the I/O over the backplane. A lot of the release schedules, if I wanted to change a card in the system, I would literally have to regression test the whole system again, making sure that everything functions correctly with each other. And it brings out new feature introduction basically on a shelf-based release schedule. Think of it as being able to then logically aggregate but disaggregate the hardware itself. So take that POTP platform and let's tear it apart a little bit. And so let's disassemble it and then logically aggregate it with software. So each blade then, like a switch blade, transport blade, is basically its own independent physical design. Space, power, thermals, I/O interfaces. Basically, this allows you to do continuous density performance improvements on each of the individual pieces in the system, much like in the SDN world, much like doing things where software is controlling different pieces. This itself allows the density and performance improvements on a per blade standpoint. And each blade is not necessarily tied to another blade. So some of the functional disaggregation values. Efficient scaling, basically low initial investment, growth basically in 1 RU increments, so giving the lowest common denominator for that function in the system. Evergreen technology, as we mentioned, continuous performance improvements. As each blade, as a new blade, new technology comes out for that type of blade, you can actually improve it. Convergence, actually rapid development on each blade, and then converging them in a common software layer, be it SDN, that allows you to tie these things together in a logical fashion. Again, pay as you grow. And the big thing is rack space utilization. As you've seen a lot of times, you walk into a central office, you see half-empty shelves. This allows you to basically utilize your rack space, your CO power, space constraints to a more better granularity in the network. Obviously, open software, optics, and architecture are key here, being able to allow the service provider to pick and choose from each of these functions the best of breed in the network. So with that, let's talk briefly about some of the multi-layer networks in the field today. One of the key things that we've seen, and it was mentioned earlier by Andrew, was OTN in the network. It provides a global, common multi-service convergent layer. Key applications include bandwidth management for 100G, lets you maximize the efficiency of that large pipe. High-capacity router bypass. We believe it can scale very high. Cost curve grows linearly with the addition of OTN, and generally provides the overall cohesiveness and makes WDM a better functional system that allows scalability of smaller rate services into the larger pipes. So with this, one of the solutions that we looked at was OTN in the metro, where we actually did a study in a large metro model where we had somewhat in the neighborhood of 40 ROADM nodes, approximately 45 spans with over 500 services that range anywhere from OC48, 10 gig E, 1 gig E, so on and so forth. And the summary of the results here was that whether you're using ROADM only or OTN with ROADM, we found that OTN with ROADM actually reduced the wavelength count by about 25% versus a ROADM only configuration. And then this actually reduced the cost in the network by about 20%. So it saved quite a bit of wavelengths in the top 5 spans that were actually deployed in this large metropolitan city that we studied. So with that, I'm going to turn it over to Jonathan at ECI.
Thank you very much, Mike. I'm going to switch gears here a little bit and talk about a few different kind of applications of multi-layer networks and our next-gen networks here. This is an example of end-to-end packet transport, and what we're showing here is how we can provide a real combination of a packet and optical services together. So for instance, in this example, we see using integrated layer 2 functionality, aggregation of multiple gigabit Ethernet and 10 gigabit Ethernet layer 2 client interfaces from business end users to the network core, in this case using 10 gigabit per second OTN pipes. Now once you get to the core, the layer 2 capabilities of the universal switch that I talked about earlier are used to complete the aggregation of this traffic and now switch it to a high-speed router over 100 gigabit per second OTN pipes. So just key points in this example that should be noted. First, we see a nice marriage of the packet and optical layers. 2, by using layer 2 statistical multiplexing throughout the transport paths, we really maximize the facility use, and finally can consolidate all the traffic into a single high-speed router port in this example, making most efficient use of this very expensive port. And we can also support connection-oriented packet transport, in this case using MPLS-TP, which enables service providers to guarantee service level agreements for their carrier Ethernet services. I now want to come back to a topic that I touched on earlier, which I believe illustrates one of the most exciting opportunities for leveraging the network for revenue generation. We have already discussed the benefits of network function virtualization for speeding up delivery of new services. What transport virtualization does, it focuses specifically on network functionality. So this can include items like broadband network gateways, evolved packet cores, even virtual routers. Now generally, the transport NFV function sits at the network edge and supports transport applications serving multiple customers. What this does is it puts the TNFV in an optimal position to marry with and support a new class of edge computing services, such as the machine-to-machine, smart city, and Internet of Things. Often these services will sit in microclouds at the network edge, and they have a specific requirement for low latency coupled with a high frequency of transactions. So this is the basis for the marriage. TNFV can go beyond providing just transport applications, but can also serve as a platform for edge computing services, taking advantage of their location close to customers. This will become a powerful tool for service providers to extract new value from their network to compete against the over-the-top delivery of centralized cloud services. And I will now hand off to some more applications to Harold.
Thank you. To conclude this section, I would now like to summarize the benefit that universal transport and multi-layer capabilities offer in networks. And basically, network studies we've done with customers show this benefit very clearly. Mike has already told us about the reduced number of wavelengths needed in a network as you use OTN aggregation versus just transparent transport. Looking at network cost in metro, this study shows a similar benefit from the use of OTN aggregation by about 20%. So this is a real-world study done with a customer. But basically, due to the bursty nature of packet traffic, we can achieve significant additional improvement by combining OTN with the statistical multiplexing of packet aggregation. This combination basically cuts network cost in half versus purely transparent transport. In a core network, traffic is already pre-aggregated. So one would think that the benefit from OTN aggregation or packet aggregation is less pronounced. But real-world examples such as this one do show you that the combination of OTN and packet aggregation still significantly improves the use of capacity in core networks as well. Here, cutting network cost by almost a factor of 2 as well, but 46% in this case. We've used network cost as a parameter here to show the benefit from universal transport, but those numbers really do show the increased network efficiency overall, and these numbers are basically are pretty well aligned with anything you do on the number of wavelengths needed in a network. And basically these results show that this type of network is really significantly more scalable going forward versus a network where you do not use these aggregation layers. So this basically summarizes and shows the network impact of the universal transport approach and concludes this section as well. Andrew, I think.
Yeah, thank you, Harold. So now I'd like to go ahead and hear from each of the individual sponsors about their specific approach to the multi-layer market and how they solve these problems. So Harold, why don't you go ahead and, well, one more thing. We've got lots of questions coming in, but if there's any additional questions, just a reminder to use the interface and we'll try to get to as many as we can. So Harold, why don't you go ahead and talk a little bit about Corient?
Thank you. As we all discussed in the webinar today, universal transport platforms are key to provide the efficiency, flexibility, and scalability that networks need today. For this reason, we at Coriant have built the first truly universal transport platform in the market. The Coriant Mterra basically combines ROADM capabilities with packet and TDM switching, and it provides 14 terabit worth of universal switch capacity in half a rack, which is, I think, quite a good footprint. It's actually an outstanding footprint looking around the market. Universal here again means that you can use every type of service in every port as introduced before. The Mterra is the latest addition to Coriant's packet optical portfolio. It includes both universal transport switches as well as best-in-class and also disaggregated DWDM packet aggregation and OTN products. Overall, the Coriant portfolio allows you to combine different transport technologies in an optimized way in the network. And this whole end-to-end universal transport network is integrated into our Transcend SDN solution that operates all of the elements seamlessly, and it ties the network into today's ecosystem of networking software, which we also looked at earlier. We call this combination of flexible transport infrastructure and transport SDN controller our Coriant Dynamic Optical Cloud. Its rather innovative and fully automated operational model unlocks the flexibility and efficiency of the universal transport approach. The Dynamic Optical Cloud enhances all aspects of service delivery, simplifies operation, and it unlocks new business models in this new world of data center network. I would now like to hand over to Mike again.
Well, thank you, Harold, but in this case it's Jonathan from ECI. But talk for a minute about our approach. So ECI delivers an elastic network. This enables service providers to control their network in real time, quickly introduce new services, and operate seamlessly in a multi-vendor environment. And the way we do this is through our 4-tier Smart Light framework. At the heart of the framework are our Apollo and Neptune packet optical transport systems and our Mercury transport network function virtualization module. These transport devices have extremely powerful capabilities. We cover complete layer 1 through layer 3 transport, have high-speed 400G interfaces, and talking about high-capacity switching, we have a 16 terabit per second integrated layer 1 plus layer 2 switch. However, these transport systems really come to life to meet service provider expectations for new services and cost reduction when they are coupled with the 3 Smart Light software layers. This includes end-to-end network management, real-time SDN control, and multiple SDN applications like bandwidth on demand that can be deployed even on the existing installed base before a full SDN NFV infrastructure is in place. And then finally, as the icing on the cake, we have a holistic layer 1 through layer 7 cybersecurity suite, which as an example could be offered on top of a dynamic VPN service delivered by an NFV. So Smart Light builds elastic networks that meet the dual challenge of not only reducing CapEx and OpEx through multi-layer optimization and virtualization, but enable service providers to deliver a rich set of new revenue-generating services. And on to you, Mike.
Thanks, Jonathan. Seems like packet optical is the watchword for the day. From a Fujitsu standpoint, we have our traditional 9500 platform, which includes a suite of access products that can deliver carrier Ethernet, OTN, up through an integrated FlashWave 9500 with switching functions, WDM, 88 wavelengths, OTN type interfaces, classic SONET SDH interfaces, and carrier Ethernet NAT also. But the one thing that we wanted to talk about today briefly is our new Onefinity, which is Access Core blade-based disaggregated functional POTP platform. And it's a family of 4 different devices, Lambda, Transport, Switch, and Access. Basically, it looks like a traditional POTP, but it's in 1RU blade functionality. Provides that open plug and play that allows you to scale your network very efficiently. Along with that, from a network standpoint, software-defined network controller, our Vatura NC can provide the SDN functionality to manage the suite of hardware products we have. Services, we have a network function virtualization for orchestration, resource visualization, policy management control. And then finally, Fujitsu is a very large services organization, and we can provide that partner ecosystem with a total integration of services, be it simple turn-up, be it install, EF&I, everything you want, monitoring, and so on and so forth. And with that, I'm going to turn it back over to Andrew.
Great. Thank you, Mike. So we'll go ahead and wrap up with a quick conclusion here and then move on to questions. I think the key takeaway from today was really that networks that are built with multi-layer hardware are adaptable, and it's really the easiest way to bring this concept of software-defined networking into the network in the near term, just by having hardware put in place that is very flexible. I think one of the important things here is that success with this architectural approach, you really need to have the right vendors that can combine both hardware and software together. We're really not at the stage where SDN is a completely open approach. You really need to go with vendors that can bring both of those tools to the table. And with that, we'll go ahead and move on to questions. There's quite a few here. I'll try to get through as many as we can. Let's see. The first question I think is a great one, and I actually had some information on some of my original slides that I didn't include. But the question is, operators have silos of packet organizations and transport organizations. And are we seeing any changes in operators that will allow them to adopt a technology that combines both of these functions? And I think this really brings up a crucial issue, is that this is not just a technology problem. This is a people and organization problem. And so I'd like to open it up to the sponsors here and see what they have to say on this subject and what sort of changes they're seeing in their customer base. Maybe Mike, would you like to go first?
I'm sorry, Andrew, can you repeat that?
Yeah, well, Jonathan, why don't you go ahead and take that question? What are you seeing in your end customers?
Yeah, so certainly this is a good question, and it's been the trend more in the past where this has actually been a roadblock towards the deployment of these integrated technologies. But in fact, the fact that we're seeing the RFPs, we're seeing the deployments that are calling for these technologies, I think is just a signal of the change that's naturally taking place in these organizations. When we talk about packet, by the way, we're talking often like today about layer 2, layer 3 VPNs. Again, using technologies such as MPLS-TP, which are more connection-oriented technologies. So it's a little bit of a crossover between the sort of traditional TDM kind of world and the packet world itself. So it is providing that kind of smooth transition rather than having the sort of pure layer 3, IP engineers, which today are still a little bit, further beyond the pale, if you like, in terms of the organizational integration. But I think transport has found a way to start to slowly move up the stack, and the education and the training within our customers is obviously being able to accommodate that.
Okay, so Mike, I mean, Fujitsu sells to a lot of very large Tier 1 organizations. No major secret there. Are you seeing that they're adapting their organizations to be able to manage both packet functions and optical functions together, or are you still seeing some separation of those organizations?
Yeah, that's a good question, and it's really a significant one because traditionally over the last 10, 20 years, there's been those silos of, the data folks, the transport folks. If you tried to get an integrated solution in a POTP that had packet functionality, the telecom side of the house really didn't want to manage it or couldn't manage it based on that. I think from what we're seeing with the advent of SDN and doing some of the new software controls, it's actually opening up, and let me also say, along with the whole network and IT function kind of merging together, that combination of SDN, that combination of convergence, I think we're seeing some new paradigms coming out where there is some openness of people to do these things, and the software tools themselves are lending itself to actually doing control in an integrated function, be it a POTP platform or be it separate functional boxes.
So Harold, Coriant also does a lot of business both in Germany and in the U.S. through Tellabs with packet optical systems. What can you share about how you're seeing your customers adapt in order to use this type of equipment?
I mean, organizationally, we do see customers bringing those different teams together and making sure that they can run their networks more seamlessly. Approaches differ, and I don't think that there's one general organization that will fit every customer because basically service providers may have very different size, very different background, very different install base, and so forth to run. So overall, we see a trend that these teams are being brought together. And as we also discussed earlier, I think these teams are also moving in closer alignment with their IT organizations than before. So overall, I think in the industry, it's become a lot easier to implement networks that actually integrate multiple different layers within one operational domain.
All right, thanks, Harold. All right, so I have another question here that I think hits an important theme, and that is that these multi-layer platforms, they're great for flexibility. They have all of these functions, but in general, they're more expensive than a standalone solution in some cases. Maybe each of you can just briefly talk about when it makes sense to use a multi-layer platform versus standalone solutions. What's your vision for dealing with the higher cost of these systems, and how do you approach that with your customers?
So this is Mike. Let me answer that first. Again, I think we've recognized that to some extent with the new Onefinity platform. We have a long-standing FlashWave 9500 that's been very successful in the marketplace. But when you do deploy that, there is an expense. You pay for the shelf, you pay for space in the CO that you may not be using, especially if you're doing like only WDM deployment or only OTN switching or only SONET type interfaces. So with the new paradigm here of being able to put out blade approaches, and a lot of this is being driven by data center, the market, the data center interconnection market, being able to provide new telco-based blades that are very functionally specific for whether it's a Lambda or whether it's a transport solution. We think you can reduce your costs and provide very specific point solutions with those types of architectures that are coming out in the network.
All right, thanks, Mike. Harold or Jonathan, would you like to jump in?
Actually,
yeah, it's Jonathan. So Jonathan here, I'll just weigh in quickly. Yeah, so there needs to be a balance between, if you like, integrating too many functions versus desegregating too many functions. And certainly we've seen this in the packet optical world, where I think we've seen a number of companies, as first attempt, put together all the optical functions, including the transport and the amplifiers and the ROADMs, stick it together, with your layer 1, layer 2 switches, and then you ended up with these beasts that just didn't know what they were. So one of the things that we've seen is some natural lines here, if you like, between the optical transport functions and the optical switching functions, which includes the layer 1, layer 2. And this is really necessary because, and it makes sense, because they share a common backplane using a universal cell-based switch. And all you're really doing over here is adding on different types of interface cards onto that. So you're not really incrementing the expense too much. But I think the real key here in terms of managing costs and what we've seen is being able to provide integrated end-to-end network management, really tying this all together. That's what's taking place today, and then tying that together in the future with the real-time control as we introduce the SDN controllers. So yes, there needs to be a balance, and I think it finds its own level.
Well, Harold, maybe you can wrap things up here?
Actually, what I'd like to do is I'd like to come back to the original question, which was really centering on, which was really more of a technology question. I think there is a bit of an understanding here, which goes back to a time when this type of universal node would be built with cascades of different types of chipsets that then add cost as you add different layers. The platform that we are talking about here basically has an agnostic switch, so that switch will first of all be able to scale to different sizes. If it's a small enough switch, you can put it into a 1 RU box. If it's supposed to be something bigger, you can actually build something bigger. Both of those options exist. But what is decisive is that this type of agnostic switch uses the same chip to switch packet and TDM traffic, and so it does not need to be more expensive than a dedicated packet or dedicated ODM platform, provided the right technology has been chosen.
All right, this is Joanne here. I'm going to jump in. Harold, thank you. That was a great end, I think a good point to end the webinar on. We are a little over, so I am going to take the controls back. First of all, I do want to thank everyone. I want to thank especially Andrew and the whole panel here, Harold, Jonathan, Mike, and the teams at Coriant, ECI, and Fujitsu for partnering on the presentation. A lot of information. I know we covered a lot of areas here. We did not get to all the questions. I was afraid of that, and I knew that might happen. Thanks, everyone, again, for sending your questions in. We will respond directly. We'll get those to the panel, and they'll be able to respond directly out to you. So thanks for participating, and thanks for joining us for this webinar. I'll mention that an archived version of the webinar will be available shortly. You're going to receive a follow-up email with more information about access to the archive. You're also going to see a short survey pop up. We'd like to have you respond, give us your feedback on this webinar, and let us know any future topics you'd like to see from the IHS team. Hope to have you join us again, so watch for more invitations from the IHS Technology Group. And that is all for this session. Thank you again for coming on, and have a great rest of your day, everyone. Thank you. Bye-bye.